Welcome to the video tutorial on intermolecular forces. Intermolecular forces are a really essential concept, and it's important that you have a clear understanding of them. Now, it's a lot of syllables, so we'll abbreviate it IMFs. What are intermolecular forces, right? This is the attraction between molecules. All right, so we have covalent bonds holding the atoms together to create the molecules. So then this is the interaction between two or more independent molecules. Now, this is the source of potential energy. And so if you're not sure what I mean about potential energy, there is a video tutorial on energy and kinetic energy and potential energy that you can refer to. So we're going to look at the three main forms of intermolecular forces. The first one is dipole-dipole. So for this intermolecular force to occur, we must have polar molecules. And so then, as the name would imply, we have one polar molecule, and it has a partial plus and a partial minus. And so then a second molecule is going to come in, and it's going to naturally orient itself to maximize the electrostatic attraction and minimize the electrostatic repulsion. So it will have an opposite orientation. Now, the dipole-dipole IMF is this attraction right here between the two molecules. All right, so it's a constant attraction. And so then if I drew in a third molecule, you could imagine how it would orient, right? Its partial negative would come in and align up opposite the partial positive. So these dashed red lines represent all of the dipole-dipole intermolecular forces. So it's the attraction that between two or more polar molecules. And we know that they're going to orient themselves to maximize attraction and minimize repulsion. Okay, now dipole-dipole I think is pretty straightforward. H bonding is a really terrible name because they're not true chemical bonds. It's an intermolecular force, and it's a case of extreme dipole-dipole. So why so extreme? What makes this special? Well, H bonding only occurs, quite naturally there's going to be hydrogen there. So if we have molecules where there's a nitrogen atom bond to a hydrogen, right, and then of course nitrogen likes to have 3 bonds, and it's a lone pair, or we could have an oxygen bonded to a hydrogen, or we could have fluorine bonded to a hydrogen. Now, what makes this so special, right? Well, when we look at electronegativities, and there's also a video tutorial on electronegativities, so if you feel like your understanding of electronegativities could use some help, I'll refer you to that video tutorial. Right, and so we remember, right, that fluorine was the most electronegative, right? So these are 3 of the most electronegative atoms or elements. And when they're bonded to hydrogen, right, remember poor little hydrogen, right? Hydrogen only has 1 proton. So it does not have a very strong ability to pull on the electrons. So what makes H bonding an extreme dipole-dipole is that we have the largest differences in electronegativity, right? This means, right, another way to say that is these are the most polar bonds, right? And then it comes down to a size thing. The small size of hydrogen allows the two independent molecules to get very close together, which strengthens their attraction. Okay, so the small size of hydrogen, right, so we have the two reasons. We have the large dipole moment, the large differences in electronegativity, so these are very polar bonds. And then we have the small size of hydrogen allows the molecules to get very close physically, right? And so these two things increase the strength of the intermolecular force to the point that we give it its own name. So, of course, they're going to be very close, but if I try to draw this, I won't be able to illustrate it if I show them too close. So I'll still keep a little distance, right? So here's a water molecule. And when we look at the water molecule, right, we can't help but see the dipole moment right here. And so then if a second water molecule comes in, it's going to orient itself in the opposite direction so that just like we saw up above for the dipole-dipole. All right, so these two water molecules are going to orient themselves, and then here comes the H bond, right? The H bond is the intermolecular force that holds these two water molecules together. All right, so it's important that we keep this straight. This right here, right, this bond right here, that's a polar covalent bond. All right? This attraction between the two independent water molecules, that's the H bonding. So it's the same idea as dipole-dipole, except because of the large difference in electronegativity and the small size of hydrogen, it gives a much stronger force. So if I could demonstrate with my hands, if as kids you ever got the chance, or even as an adult, if you had two bar magnets and we held the bar magnets far apart, then that will symbolize the charges, right? And so if I have these two magnets far apart, one magnet does not feel the other magnet. But now as I bring the magnets closer and closer together, we start to feel that electrostatic attraction or repulsion, or the magnetic attraction or repulsion. And as we get closer and closer together, finally we get so close that the attraction just overcomes and they'll get stuck together. So that's what happens with the small size of hydrogen. The molecules are allowed to get super close, which strengthens their attraction to each other. Alrighty. So now we'll look at one more type of intermolecular force, and this is called the London force. And this one is interesting because, first of all, this one has a bunch of names, all right? So it's also called a dispersion force, and in most of the biology texts, it's referred to as van der Waals. It also gets called an instantaneous dipole, or it gets called induced dipole, or it gets called a hydrophobic interaction. So this intermolecular force goes by a lot of names. So depending on how you hear it described, it's all describing the same intermolecular force. And what's important about this one, right, it's for non-polar molecules. Now, this may seem very strange because when we talked about dipole-dipole and H bonding, it was all about having those differences in electronegativity and the partial positive and partial negative charge. So how in the world does this dipole work? Well, let's say we have this large non-polar molecule. So let's think back to what we know about the structure of atoms and molecules. When we have the nucleus of the atom, and let's say we grow it up to be the size of a grape, right? So if the nucleus of an atom is the size of a grape, the electrons can be up to a mile away, right? So if I'm holding the nucleus of an atom in the palm of my hand, and it's the size of a grape, the electrons could be all the way to Highway 99, Broadway, Fruit Ridge, and I-5, right? There's a lot of empty space inside of atoms and molecules. And the electrons are busy whirling around. So what can happen in these nonpolar molecules is for just an instant, we have like an electron pileup, a little electron gridlock right there. But then that means if the electrons are piled up over here, there must be some electrons missing over here. But it's a very weak, instantaneous effect. So now, if there's a neighboring molecule that's also nonpolar, right? But as soon as we get some chaos over here, if there's a partial positive here, the electrons in this nonpolar molecule, they just get all excited and attracted to that positive charge and they rush over. And if those electrons rush over, that means they're missing from somewhere else. And so just for a moment, we are going to have a very weak, very temporary dipole moment. So that's why sometimes it's called induced, because it ripples through. It also gets called dispersion because the more surface area we have in a molecule, the larger the molecule is, the more likely there's a chance that we'll get some electron anarchy here and get one of these instantaneous dipoles. And van der Waals is the name of the gentleman that first proposed this. Alrighty, so now notice, right, these are nonpolar molecules. So if we come back later in time, right, there's no permanent dipole moment. So just because there was a partial negative here a while ago, that partial negative could have moved. And then maybe the partial positive's over here. And then that would induce a dipole here that could end up with a partial negative there. And so then once again, we get a very weak attraction, a very temporary attraction between these nonpolar molecules. And so the larger they are, the more dominance this London force will have in keeping the molecules attracted to each other. So now that we're familiar with the three primary intermolecular forces, let's look at their relative strength. All right, so we'll put the strongest over here. All right, so of course that's going to be H bonding, right? Because that's our extreme dipole-dipole. That's the largest intermolecular, or the largest dipole moment with a small atomic size of hydrogen. And then that will be greater than the dipole-dipole, which still has the permanent dipole moments, but they're not as strong. And then, of course, the weakest is going to be the London, where they're temporary. Alrighty, so now I would like to give you an audio version of intermolecular forces. Alright, so with H bonding, it's highly polar, really large. So if we think about H bonding, it would be like, oh, right? It's really strong and it's a constant attraction. Dipole-dipole, on the other hand, it's a weaker dipole moment, but it's constantly present. So that would be more like, oh. And then if we look at London force in terms of an audio experience, it would be like, ah, 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 ah. Very weak and temporary, right? So H bonding is constantly present and strong. Ah, right? Dipole-dipole, constantly present but weaker. Ah. And then last but not least, London, ah, 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 right? And that is representing the potential energy that is holding these molecules to each other. So, when we look at molecules, we want to be able to identify the dominant intermolecular force. So the first thing we're going to ask ourselves, right, is polar or nonpolar? So if we look at this molecule here, we want to see it in its three-dimensional shape. And we recognize that there are polar bonds, but they're all radiating out into the corners of the tetrahedron. So even though we can write dipole moment arrows, overall the molecule is nonpolar. And for all nonpolar molecules, the dominant intermolecular force is the London force. Now this next molecule, right, it's really important to remember your three-dimensional shapes. So if you're wondering how I jumped from this Lewis structure to this shape here, you're going to, I would encourage you to watch the molecular shape video tutorial. So here we recognize this molecule is also in a tetrahedral shape. And so now we have our two dipole moments. They're pointing in the same direction, so we end up with a polar molecule. Once we have a polar molecule, we need to ask ourselves, is it dipole-dipole or H bonding, right? So this one's easy. There's no way that we can have H bonding here because there are no nitrogens, oxygens, or fluorines. So we would describe this as dipole-dipole. Okay, now we look at our third molecule. Remember, with carbons and hydrogens, they have similar electronegativities, so we never draw dipole moment arrows between carbons and hydrogens. But oxygen is to the right of carbon, and so we get a dipole moment there. Anytime we have a molecule with only one dipole moment, we know it's polar. Okay, now this one could be a little trickier. We have oxygen and we have hydrogen, but they are not bonded to each other. So once again, this is an example of dipole-dipole. Now we'll look at the last example, so we can compare our third example to our fourth example. Here, right, we'll always ignore, there's no polarity that's significant between carbons and hydrogens, so there's no dipole moments there, right? But here we have, between oxygen and hydrogen, we have a very large dipole moment. And then between the carbon and the oxygen, we would have a small dipole moment. So this molecule is definitely polar. As soon as it's polar, now we see, yes, right? We have our OH bond, which lets us know that the dominant intermolecular force here would be H bonding. Okay, so it's important to make the distinction between example 3, where oxygen is present, versus oxygen being bonded to hydrogen in this last example. Alrighty, so let's have one last page to apply, show a couple examples of where intermolecular forces come in, and one little practice problem's left. Okay, so are the following pure compounds capable of H bonding? So if we look at this compound A here, we see, right, we see NH bonds. So we would say yes. For this second example, we definitely have oxygen, right? And we have hydrogen, right? But there's no OH bonds. So we would say no. No H bonding. And there's hundreds of examples of how intermolecular forces show up in our biochemistry and physiology and everything. So just a quick little teaser to hope have you feel motivated and passionate about intermolecular forces because they're so important. Basically, the two strands of our DNA that create the double helix, they're held together by H bonds. It's like a zipper. And so we will be studying the structure of DNA later in the term. But here are the nitrogenous bases. And so these dashed lines here, these are the H bonds that hold the two strands of DNA together. And so now if we circle in to where we have cytosine and guanine, so we get a closer view of the DNA, we can see here, right, here is our NH. So when we see this, we see a partial plus on the hydrogen and a partial minus on the nitrogen. And then nitrogens are electronegative, so there's a partial minus. Here's another partial minus on this molecule. All right, and now we'll look at the other nitrogenous base. Right, oxygens are very electronegative. When you see them, they're going to have a partial minus. Hydrogen, partial plus, partial minus, partial plus, partial minus. So here we create, here are the H bonds. So this hydrogen with its strong partial positive is going to be attracted to the oxygen with its strong partial negative. And then the same thing happens here and here. So there are three H bonds that keep these two, that help to lock together our DNA strands. And so then it becomes like a zipper. So we can open and close our DNA by either breaking these hydrogen bonds or reforming them. So there is an overview of the fundamentals of intermolecular forces. So this would be a good time to go back through your notes and work a couple homework problems to reinforce your understanding.